Welcome to this presentation on Inside the Atlassian OnDemand Private Cloud. My name's George Barnett and I'm Atlassian's SaaS Platform Architect. About 2 years ago, a team of engineers looked into the way we were hosting our software and we decided that it was really inefficient. So we set out to reimagine this in our secret lab, which was above the pub pictured there, and we came up with a brand new solution to how we did our hosted infrastructure. There are a number of problems which we hope to solve, and I'm hoping to take you through some of those problems, some of the challenges we faced, and some of the solutions that we've developed while we were implementing this project. I'll give you a bit of a sneak peek. We did a soft launch a year ago, and by the time we did our hard launch, we were at 1,000 VMs. And then now recently, a couple of weeks ago, we were at 13,500 VMs. That's 13,500 customer instances. That's actually around about 65,000 JVMs on our platform. Now, the first thing that people say to me when I say, well, we reimagined our cloud, is they kind of go, well, we have a cloud, so what? We also had a cloud, and we also had all of the problems listed on this slide. We had VM sprawl, poor performance, over-provisioning, slow deployments, low visibility into the stack. And the reason for that is really because virtualization creates new challenges, but it doesn't do anything about the existing ones. So what do I mean by that? Well, if you have 200 machines and you don't have a system or process or tool to manage those 200 machines, when you introduce a virtualization solution, you're going to have 800 machines or 1,000 machines, and you still won't have a way to manage them. I've seen situations where there was a master Windows virtual machine that people would just duplicate and then start up a new machine. Pretty soon they'd have a couple of hundred Windows machines that they had no idea how to manage. One of the problems is also that a lot of virtualization tools kind of look like this. Now, depending on the job or the problem you're trying to solve, that can be very useful. But in our situation at Atlassian, with our hosted platform, that's really not the problem we were trying to solve. We wanted our platform to look a little bit more like this. We needed a specific tool for doing a very specific job, and we were hoping to gain a lot of efficiencies that using that specific tool would give us. The first thing I want to talk to you about is focus. In terms of infrastructure, what does this mean? Well, it means be less flexible about what you provide. On the Atlassian platform, we say you can use any database you want as long as it's Postgres 8.4. This is quite important. You don't have to be everything to everyone. We do have other clouds within Atlassian, notably with our IT department and our building engineering guys, and they have very different needs. But for our on-demand platform, we can sort of leverage these efficiencies. So we only provide one database, we only provide one app server, we only provide one type of operating system. This lowers the operational complexity that many of our teams face, and it provides an opportunity for us to give teams that are depending on us this really in-depth tool chain that they can use to manage these services that we provide. It also means that the developers and QA engineers have this much smaller test surface matrix which they have to test against. The other thing that focus means is learn quickly. I left fail fast in there, that's what I originally put in, but I think it's a little bit negative. I don't like this idea of lurching from failure to failure. I prefer lurching from learning experience to learning experience. It's a little bit more positive, and it kind of really reiterates what you should be doing, which is learning, not trying to just fail. How do you do this? Well, you do as little as you possibly can, and then you deploy it and you use it. And then you go back and you do as little as possible, and then you deploy it again. There have been many situations where we've done a very small amount of work, thinking that we would have to do a huge amount of work. But that small amount of work has lasted us for a very long time. Now that has two benefits. The first is that we got to go and focus on something else that was more important to us. And the second benefit is that we got to spend the time between when we did the first solution and when we needed to do the second solution, which might have been 6 months between that. We got to spend all that time really learning about the problem in a much deeper way. When we started the project, we also had this methodology. We started it with Block 1. Now, Block 1 was a small-scale model. It was 4 desktop machines, and it was really there just to validate our design, the initial architecture, and to validate that everything wouldn't fall over. Where did we get the name Block 1 from? Well, if you're a space geek, you'll know about what NASA were doing with the Apollo program. They created the Block 1 spacecraft, and they were these limited production flight weight spacecraft, but they were used to verify the production spacecraft's structural integrity. They also verified systems operation and systems compatibility. Sadly, Block 1 caught fire and it killed all of its crew, which was very bad for the crew, but nonetheless a very valuable learning experience for NASA. In terms of our Block 1, we didn't have anywhere nearly as bad experience. We had a bunch of our goals validated, so our apps didn't fall over and our network boot assumptions were validated, but we did find out in Block 1 that our creations of our virtual machines over NFS was far too resource and time intensive. I'm going to cover this a little bit later. Block 1 led us on to Block 2. So in NASA's terminology, Block 2 was all the lessons they learned from Block 1 baked into a new hardware design. All the manned Apollo missions from that point on were actually built on a Block 2 design. They modified it slightly throughout the years, but the basic design was still a Block 2 design. That's what went to the moon. For us, it was a much bigger environment. So we went from having desktop machines to having a couple of really, really big servers. We wanted to validate hardware resources being used for customers, and we also wanted to validate which CPU vendor was going to be best for us. We were quite successful in this. Our customers per gigabyte of RAM metric was validated. We validated that we could actually get as many customers as we thought onto the machines we bought. And we also validated that our distribution tools and our failover tools worked. We also validated which CPU vendor to use at that point in time. It was Intel CPUs versus the AMD Bulldozers, which were 12 cores versus 6. And we eventually settled on Intel for our particular workload. One of the things we did learn, though, was that our initial assumptions about how much RAM we needed in a machine were off by 50%. We started on 96 gig of RAM in a machine, and we did that because with 96 gig of RAM, you would get a much higher speed the RAM would run at because the banks weren't full. We then went to 144 gig of RAM, and we tested the applications for performance and got the same performance. Now, we hadn't expected this because when you run 144 gig of RAM in the configuration we were running, it causes the RAM to run at a slower speed. We thought this would impact our applications, but in performance testing, we found it didn't. That means we got 50% more RAM into our hardware. That means the overall cost came down by quite a significant amount. So, talking of hardware, the existing hardware we had was a pretty poor fit for our workload. This is often the case with many cloud providers. Cloud providers give you a virtual machine and you can use it, but you don't really know what the underlying hardware is. And the underlying hardware is not actually tailored for your particular workload. In our workload, we found that memory and I/O were heavily constrained, but CPU wasn't. This was because the original machines that were bought had 36 gig of RAM, and that might have been fine on maybe a general computing workload. But on our particular workload, we found that in order to get the density we want, we were loading up way too many virtual machines per physical machine. This means that they were spilling over into swap on the actual hypervisor, so you're swapping to the local disks on that particular machine, and inside the virtual machine you're also spilling over into swap, and that was going out to the SAN. So that was causing a huge amount of disk I/O both on the SAN and on the local machines. One of the other problems with running Java inside a virtual machine is that if your JVM is idle for a while, what will typically happen is the operating system will swap out to the old gen. Then a couple of requests will go through, and the garbage collector will come around and want to garbage collect the old generation. So it'll pull all that memory up off disk, causing a huge amount of disk I/O if that's been swapped out, only to throw it away. One of the problems we also faced on our existing hardware infrastructure was that it was all installed by hand. So we had 15 machines in a rack with a SAN. That was all in one rack. They would show up in 16 boxes, plus a bunch of boxes for the disk. Somebody would have to go into the data center, unbox 15 machines, rack them, cable them, unbox a SAN, put all the drives in, rack it, cable it, configure all the boxes, configure all the SAN, get it all working together. This took time, around about 2 weeks, but it was certainly a problem because whenever we wanted new hardware, there would be a 2 to 3 week lead time while we waited for the machines to arrive and then somebody to actually get them into the racks. So what did we do? Well, to deal with our resource utilization, we took 6 months of existing monitoring data from the platform. We also went and introspected a lot of the processes to work out what their idle state was, what their peak state was, how much CPU they were using, and how much disk I/O they were using, and how much network I/O they were using. We took all of this information and we came up with the ideally sized rack. So what does our ideal rack look like? Well, it's got 10 compute nodes, 144 gig of RAM in each of those compute nodes with 12 cores. There's no disk in any of them. We've got 3 storage nodes on each of the racks. That's got 24 disks per storage node. Each rack comes completely assembled. All we have to do is unwrap it, provide power and networking. We go from rack on the floor to connected and in use by customers in around about 2 hours. There's a couple of advantages to using a systems integrator. The first is that it's reliable. We don't have to burn in the machines because we found that the systems integrator takes care of all of this for us. In this picture you can see a bunch of guys at our systems integrator, Silicon Mechanics. They're putting the machines onto the workbench and they're going to go through a 2-day burn-in. We don't even get to see the machines if they fail. The other advantage is that it's neat. Now this is going to depend on who's doing your cabling, but often if somebody's doing a poor job of cabling, you won't know about it because you might not be in the data center. In our case, our systems integrator takes care of all of that for us. All of our cables are neatly labeled, so if anything jiggles loose or pops out for some reason, it's easy to know where it's meant to go back into. It's also very consistent. You can see a picture of 4 racks on the loading dock here, and they're going to be shipped out to us soon. You see the 10 compute nodes and the 3 storage nodes at the bottom of each rack, but they're all the same. We currently have 34 racks, and they're all identical. And as I mentioned, it's really easy to deploy. This picture is taken inside the data center with a forklift basically just bringing the rack in. We're going to put it down, bolt it to the floor, give it some power, and off we go. So I mentioned no disks, and usually people kind of go, wait, what? What do you mean no disks? Well, our existing compute infrastructure used local disk for swap and for the hypervisor boot. So once we got the resource utilization correct, we no longer needed to swap. That just means we had to keep the local disks for the hypervisors to boot. But that's a lot of infrastructure just to boot off. So if we take our rack, which is 10 compute nodes, and you say that, well, we need nice reliable disk and we don't want to have to mess around with some sort of software RAID, that means you've got 20 disks, because you need a pair of disks in each machine, and you've got 10 RAID cards that you now have to deal with. That's a huge amount of hardware when you start to multiply that out by 30, 35 racks. And you've got to spare that, you've got to worry about it failing, you've got to monitor it, you've got to pay for it. We wanted to come up with a different solution. We ended up with no disks in our compute infrastructure. How did we do it? Well, firstly we evaluated booting from several different methods. We first looked at USB drives, and we looked at NFS. The problem with those is that USB drives are unreliable and slow. Not only that, you're in the same situation you are with regular drives. Modern server class machines have a USB header on the inside of a machine that you can just pop a USB drive into, but it's got to be reliable. You've got to basically have it in RAID. You've got to go and get in there and replace it if it fails, and you have many of the problems that you still have with a spinning disk. You still have a physical piece of hardware. We looked at NFS, but the problem with NFS booting is that it relies on an NFS server being there all the time. If the network goes away, the whole machine dies and everything croaks up. You've got to generally kick the machine to get it back to life. So what we settled on in the end was this custom binary init RAM disk as an image, as well as a kernel. So let's talk a little bit more about that. The image is a 170 megabyte gzipped file system. It's downloaded on boot by Etherboot, which is part of our boot process, and it extracts it into RAM. It uses about 400 megabytes of RAM, which is a significant amount, but not a huge amount when you compare that we've got 144 gig in each machine. The great thing is that there are no external dependencies after boot. Once that machine is booted, you can unplug it from the network. It's just like a regular Linux machine. It's just a complete toaster. As long as it has power, it's fine. We boot all of our compute infrastructure from the same image. This is really good because it allows us to boot to a known state. All of our hardware is running an identical image. If one machine misbehaves, we just power cycle it. If it's still misbehaving, then it has to be a hardware problem because there are another couple of hundred machines that are not having that same problem. How does the process work? Well, first of all, you boot the compute node and you set it to PXE network boot. It calls out to a boot server and gets a DHCP response. It then goes and grabs GPXE over TFTP, and GPXE then loads and does another DHCP request and response. You can use conditional statements inside DHCP server daemon, and that allows us to detect the different calls from both PXE and GPXE. When GPXE calls, we serve up and say, go boot from this HTTP server using this script. That boot script contains a location of a kernel and a boot image, and etherboot GPXE takes care of the rest of it for us, and up it comes. There are a couple of sharp edges doing it this way. The first one is that you have no swap, so you need to provision carefully. This is not really a big problem if you've got a heap of RAM and you automate your provisioning. Each machine in our infrastructure is quite defensive, so it won't actually start a virtual machine if it thinks it doesn't have enough resources to service that request. The other thing is you've got to treat your hypervisor image like an appliance. What does that mean? Well, if you want to gain those benefits of having every machine identical, you shouldn't be changing any of the running code on that hypervisor image while it's running. You rather rebuild the image and reboot your infrastructure. This is quite a heavyweight operation, so if you find yourself doing this too often, it's probably a sign that you have too many services inside your hypervisor. This brings us to the software that we use inside our on-demand platform. The first challenge we faced with this is really that virtualization can be quite efficient. There is a penalty with CPU and a penalty with memory to running lots of virtual machines. It gets better over time as new instructions are implemented in the hardware, but it's still there. This led us to OpenVZ. What is OpenVZ? Well, if you've used FreeBSD jails or Solaris zones, it's a very similar technology. It's a containerization solution for Linux. It existed before LXC, and sadly LXC is still it's not quite there yet. It's going to be there at some point in the future, but it's still got a bit of work remaining to make it root safe. OpenVZ is the basis for Parallels Virtuoso containers. It's the open source version of that. There are no guest OS kernels in OpenVZ. You don't have to run guest OSs like you would with a normal hypervisor solution. There's no performance hit because of that, and there's much better resource sharing. So let's look at the performance. Well, this is a slide from the OpenVZ wiki. You can see here OpenVZ in the orange and the red, and it is outperforming the others by quite a long margin. Along the bottom, we're showing compute workload, basically, 5 units, 1 unit, 5 units, and 10 units. And along the left, you can see the amount of throughput. So this is a vConsolidate benchmark. It simulates Java and a database, and it's all running on one machine. So you can see as we ramp up the amount of work that this machine is doing, you can see that OpenVZ just keeps going. One of the other benefits with OpenVZ is because it's a Red Hat kernel with some patches applied to it, as upstream kernels get faster, we see those benefits. So you can see this in the red there, where OpenVZ, with the newer kernel, as opposed to the orange, is actually getting faster when we ramp up to 10 units. This benchmark over here is representing DVD store performance. It's a LAMP-based benchmark, so Linux, Apache, MySQL, Perl. It's worth noting in this slides, in these pictures, that orange is not OpenVZ, red is OpenVZ, orange is actually Windows Hyper-V. So you can see in the left side of things, OpenVZ, again, much higher requests per second as we ramp up the number of containers running. And in the right-hand image, you can see OpenVZ's response time remaining low and stable as we ramp up the number of containers. The next thing OpenVZ gives us is resource deduping. Now, it doesn't naturally give it to us, but there's a couple of things we can do to make this better for us. What is resource deduping? Well, to me, it really means don't load the same thing twice. And that's kind of one of the challenges we faced, right? JVMs certainly aren't lightweight. And when you're running 65,000 of them, it's quite a challenge. Full virtualization does a poor job at this. If you have 50 virtual machines, it means you have 50 kernels and 50 caches and 50 sets of shared libraries you need to load. Memory dedupe combats this, but it burns CPU to do that. And often it can't do it in user space within the guests. It's only going to scan the kernel space. So it's going to be able to deduplicate things like the kernels and some of the caches and the shared libraries. But if there's anything else that's possible to dedupe, you might not get those benefits. It also is meant to work across all operating systems, which is really, really good if you need to run lots of operating systems, but you're paying a penalty for this flexibility. We didn't need that flexibility, so we were able to exploit some Linux-specific features. Well, firstly, OpenVZ containers all share the same kernel, which means if you could somehow provide a single OS image to all your containers, you'd get some free benefits. You'd only load your shared libraries once. Because the same blocks were underneath each container, you would only cache each of those blocks once. And you would have the added benefit that your operating system image would be the same across every instance. This brought us to our challenge. If all containers are the same operating system image, then managing state on them is going to be an absolute nightmare. One bad change in one container would just break all of them because it would propagate straight across. We thought, well, managing state on multiple machines and containers is kind of a solved problem, right? But what if you have more than 10,000 machines? We're at 15,000 at the moment, and that number is growing really, really quickly. And we also thought, well, why are we modifying the operating system anyway? I mean, your phone doesn't upgrade when you install a new app, right? We came back to a mantra that we've been using in our team for a long time, which is simply fix problems by removing them, not by adding systems to manage them. This led us to read-only operating system images. How does this work? Well, if you examine the data in your system, you'll find there's probably three classes. There's the operating system and daemon code, there's the application code, and there's the application and user data. Those are three distinct things. Right at the bottom, we have an OpenVZ kernel, right? On top of that, it starts a container. So inside that container, we have the first subsection of the data. That's the operating system tools, the daemons, and that sort of supplied code that's vendor supplied with your operating system. We put that into the root and we make it read-only. We don't actually start any services at this point in time though. So your operating system comes up and it's got nothing started. It's just a completely blank container with really only init, syslog, and cron running. We start nothing else. The next thing is we provide into that same container a place for applications, JVM configs, and self-written code, and the code that we manage. We mount that onto /software. It's also read-only. So there's a subtle difference between the two of these. The operating system tools and that supplied code is read-only to everybody. It's considered immutable across the entire cluster. However, the software tree is not. The software tree is actually writable to the deployment tools on our deployment servers. So people can deploy new software and we're continually overwriting and the tree is continually changing. However, with the operating system tools, it's not changing. Once you have a version of the operating system, that version is considered immutable. And if you want a new version, you have to create a new version in a new directory and version it. Back to our example. The next thing you need is somewhere to put your application and user data. We put this on /data and we persist that over NFS to a read-write volume. Finally, you need to start services. So each container has a copy of daemon tools running, and daemon tools looks in /data/service so it can know what services to run. When a container comes up, we install some operating system services into this location. That's things like SSH, perhaps a database, as well as monitoring tools. Then, when we install the services that the customer has purchased from us, Confluence or Jira or maybe Bamboo or Fisheye, we put that into /data/service. This way, when the container restarts and daemon tool starts up again, it knows what services it needs to start because that's persisted onto the read-write volume. So how do we do that? Well, this is for the technical guys in the audience. Effectively, what you do is on your storage infrastructure, you create two exports, a read-only export and a read-write export. You build an operating system distribution inside a chroot somewhere. Doesn't matter what tools you use to do that, as long as you use some sort of automation. And you take that tree and you put it inside the read-only location on your storage infrastructure. Next, you make a data directory somewhere in the read-write location, and that's where each container gets their own data directory that it can persist data to. Then, this is the important part. When you start a container, you bind mount that operating system image that you've chosen into the root. So OpenVZ has a default root in /vz/containerid/root. You bind mount that image on top of that. The reason you bind mount is so that each operating system is always backed by the same blocks on disk. This allows the Linux caching infrastructure to not have to store multiple caches. You save it only once. It also means that when you load the shared libraries, it's the same blocks on disk, so the kernel only loads those shared libraries once. The next thing you've got to do in your mount scripts is replace etc var and temp with some defaults on a memory file system, because Linux expects to be able to write to these. The final thing you do in bringing the containers up is you mount the data dir to /data. That gives your container somewhere to persist their data that they need to persist. There's a few more benefits to doing this. Firstly, you can now distribute your operating system images as a simple directory or a tarball. You can prove that your environments are exactly the same by running the identical image, and as you move that image from data center to data center, you know it's exactly the same because you can MD5 it and you can prove it. Also, because it's just a directory on disk, it's really just a variable in a config file somewhere. So each container has its own config file. There's a variable inside there that says, I'm running this particular operating system version. If you want to roll forward to a new version, you change the variable and you reboot the container. To get a deterministic rollback, you change that variable back to what the previous version was and you reboot the container. So you can flip between OS versions just via this simple method. The final thing I want to share with you today is one of the quirks of one of the things we learned while we were doing this, and that's the swear wall. Your team often knows what's hurting it. You have all these tools that you're using, and you usually encounter a few that are really not that great for team morale, and you know they're hurting you. The swear wall helps you quantify that. How does it work? Well, you have a whiteboard. Every time you swear at a piece of technology, you put a mark on the board. Pretty simple. So, person swears at Solaris, Solaris gets a mark on the board. You repeat, and then you periodically throw out your offensive technology. This is very, very effective in cutting the craft in any infrastructure. If I can leave you with just two things I'd like you to take away from this presentation. The first one is optimize for the task at hand. Don't get caught up too far into the future. The future's problems are the future's problems. Really optimize for what is happening now. The other thing is, don't layer solutions onto problems. Just get rid of them. Thank you very much, and I hope this was useful to you.